Okay, so last time we started our journey here through chapter 14, didn't get too far. And this is about acids and bases we talked about. And a reminder, sort of definition of an acid is really something that can produce, bless you, H plus ions in solution. Remember as well, H plus, which is a proton, a hydrogen ion, and also H3O plus, which is the hydronium ion, are essentially the same thing. So they can be used interchangeably. And what we're talking about when we talk about an acid, that ability is again to produce that H plus that is again free floating in the solution, not attached to anything, just the ability to release that into the solution so that those H pluses or H3O pluses are basically floating around. A base, on the other hand, is something that can produce OH minus in solution. And it's the same idea. It's something that's able to produce, once again, kind of free floating hydroxide ions in solution. As we'll talk about, obviously, the relationship of how much free H plus you have in the solution to how much free OH minus you have in the solution will determine whether or not, for example, the solution is acidic or basic. These were sort of a general definition, and remember that in terms of bases, for example, and even acids, there are sort of strong versions of acids and weak versions of acids and strong and weak versions of bases. Not all bases have hydroxide in them, but a lot of our strong ones do. A more generic sort of definition of an acid and base was the Bronsted-Lowry definition. And in a Bronsted-Lowry definition, an acid is a proton donor. So that is something that will give away basically an H plus. And a base is a proton acceptor. Will accept the H plus. So kind of add the H plus minus an H plus. And the sort of consequence of the Bronsted-Lowry definition of acid and bases is when you create an acid plus a base, you will end up with, on the other side, partners to those acid and bases, and those are known as the conjugate acid and the conjugate base. Now, these are related to each other really based on the definition of an acid, which is going to send over the H plus, basically. And that is actually the only difference that there can be between, say, the acid and its partner on the other side, which is the conjugate base, or the base and its partner on their side, which is the conjugate acid. The only difference can be just one H plus. So if there's anything more than H plus difference, one H plus difference, then it is not a partner or pair. The acid, obviously, because it loses an H plus, will have one less H plus as it goes over to the conjugate base side. And the base, since it's going to accept the H plus, will have one more H plus as it goes over to the conjugate acid side. So again, these things are related to each other. Only difference that one H plus. Any questions on the stuff we started talking about last time there? All right, so I think we laid it up there at the example. I don't think we did the example, so let's do the example now. Which of the following pairs here? Okay, so let's take a look and see. We'll start with the first pair here. We got basically HCl, and we got a, I don't like how they always write that. I'll go ClO minus, which is the same thing. All right, so in this case here, the difference is one H plus, right? But it's also a difference of oxygen that the other guy doesn't have. So that would mean that these guys would not be pairs. Again, the difference there is more than one H plus and or something else, so it cannot be. We look at the next one, which is a little sulfuric acid and a little sulfate. Are these guys partners? The answer is no, they are not partners because the difference here is actually 2H plus difference, right? So again, it can only be 1H plus difference at a time. We take a look at the next one, which is ammonia and NH3. The difference here is that actually is just 1H plus. You can either take the H plus off of the NH4 and you'll end up with NH3, or put the H plus on the NH3 and you'll end up with NH4. So that is a winner there. And here we have H3O plus and OH minus. Are they partners? Again, they are not going to be partners in this case because the difference here is probably like 2H pluses, right? Which is too many. So not partner either. And obviously that one's not true. So it looks like number 3 here is the only partner. So you may say to yourself, aren't these guys related to each other? And the answer is they are related to each other, but they are not related to each other as acid conjugate base pairs. That is because sulfuric acid, for example, is a diprotic acid, which means it actually does have 2 hydrogens that will come off. The hydrogens actually do not all come off at once. It's like a stepwise sort of fashion as to how the hydrogens come off. So for example, here, H2SO4 will drop 1 hydrogen and make HSO4 minus. Then that HSO4 minus will drop a second hydrogen and make SO4 2 minus. That is why when we look at this, the partners in terms of acid and conjugate base pairs, this guy here and this guy here, they are partners, as that is only a 1H plus difference. If we look at this guy here and this guy here, they are also would be partners, as that is 1H plus difference. But as we had in this problem, jumping from here directly to here, not good because, again, that's a 2-step fashion. Any questions on that there? All right. So, by the way, is it easier to remove the first hydrogen or the second? Which one's easier? First one's much easier, right? Because you remove the first hydrogen. Now you have a negatively charged thing that you want to remove. Something that's positive, so it's much harder to pull it off, right? So always the first one there is going to be much easier. Any questions on that there? All right. So we have aniline here. What would be its conjugate acid to this base? Assuming the right answer is up there, hopefully, maybe. We're understanding the relationship that we talked about a second ago in terms of Bronsted Lowry can come into play and be sort of handy. So we basically, as we talked about, have acid and bases on the left-hand side, conjugate bases and acids on the right-hand side. And again, the relationship here, acid on one side related to the conjugate base, base on one side related to the conjugate acid. So not all problems like this will be nice to tell you that it is a base. They will just say, hey, what is the conjugate acid for this particular thing? So if you understand that you are looking for the conjugate acid in this case, and you work your way backwards, that will tell you that what you are looking at is a base. And basically, you just have to follow the definition of a Bronsted base, which is something that will accept the H plus. Hopefully, you should know that's what you should do, either put an H plus on or take it off. And in this case, that's what we would want to do in this case, which is stick on an H plus. So here we're going to add 1H plus to it. And remember that we're also adding the plus part of it. So it should have the charge on it as well. That looks like number 2 there on the list. Yeah. Question on that there. So if we had something like this, a little HCO3 minus, write the conjugate acid for it, and also write the conjugate base for it. See what you come up with. Starting with the bicarbonate in each case. All right, so let's take a look. We'll start with the conjugate base. So once again, if you're not sure, we know conjugate base is over here. That means if we think about backwards of what we're starting with, what we should be looking at in this case is going to be acting as an acid. And the definition of Bronsted acid is something that will donate the H plus. So basically, as we come this way, we want to take off the H plus, and that will give us CO3. Remember that when we lose the plus, we become one more negative. So we're already -1. So now we become -2 in this case, which will make us carbonate pretty much. Question on that one there. Now, if we're looking for the conjugate acid, much like in the previous problem here, if we go backwards, once again, that tells us that in this case, it's going to be acting as a base, which means it actually should accept the H plus. So we're going to put that on. So that will give us an H2CO3 plus 1 minus 1 gives us 0 in terms of the charge. So that's how we get to neutral in this particular case. Any questions on either of those there? This is, as we can see here, something that can act as an acid or base. Things that can act as an acid or base are what are known as amphoteric. A lot of times when you have a substance like bicarbonate or anything like that that has an H and also has like a negative sign, a lot of times they could go both ways. It could act as an acid or a base depending on the situation that's occurring in that particular reaction that you're doing. Water as well could act as an acid or a base. It can either gain or lose an H plus as well. Any questions on Bronsted, Lowry, acid, and bases? All right, then speaking of water, let's talk a little bit about water. Water, as I mentioned, can act as an acid or base. It's amphoteric. It can also react with itself, which is sort of constantly happening when you have a solution that's water-based. One water will act as an acid, one will act as a base. So for example, here, this guy is going to grab its H plus, so he's going to act as a base, he'll act as an acid, and then obviously we'll have our conjugate acid base pairs on the other side, with this being our conjugate acid, and this guy being our conjugate base. This is actually an equilibrium type of reaction that's occurring when we have water basically reacting with itself. And because it's an equilibrium type of reaction, we could write an equilibrium expression, which is our favorite. This is oddly known as Kw, which stands for water ionization, basically. And it's the same thing. It is products over reactants, so concentration of H plus times concentration of OH minus. Here, just like we talked before, we would not include the water as it is a pure liquid, so we would not include it. That actually has a value at 25 degrees of 1 times 10 to the minus 14. It does change with temperature, but for the most part, in most chemistry classes that you use, Kw4, you can almost think of it as a constant that doesn't change very much, but it does change, again, with temperature, if the temperature happens not to be 25 degrees. And usually if you have come across a problem like that, they will kind of give you the kind of new value for Kw at that particular one, or refer you to a table to look it up. But other than that, if you have to use Kw, pretty much that's going to be the number that you see. So this is good because we can actually use this Kw to help us determine whether or not a solution will be acidic, basic, or neutral. So our Kw expression, which is our H plus times our OH minus, equals our 1 times 10 to the minus 14. Once again, this is another equation that if you wanted to, you could just substitute H3O plus in there for the H plus, and it's the same thing. Again, I personally use H plus most of the time, but again, books will use H3O plus there. And it's really just the acid part. So you can think of obviously the H plus or H3O plus as the acid part of the solution, and the OH minus is kind of the base part of the solution. So you could use this to solve for the concentration of the H plus or OH minus if you know the other. And if you solve for them and they do equal each other, you end up with an H plus concentration that equals an OH minus concentration. By the way, that would be in this case something like 1 times 10 to the minus 7 molar for each of them. That will be a neutral solution. If you calculate the H plus concentration is larger than the OH minus concentration, you very much have more acid floating around there, more H pluses than OH minuses. That's going to make the solution acidic. And opposite is true if you calculate that there is more OH minus ions in that solution than H plus ions, then it will be basic. Obviously, the good news on the rearrangement here is it's pretty much the same regardless of which one you got. H plus would be Kw divided by the OH minus, and the OH minus would be Kw divided by the H plus. So it's really the same calculation, just regardless of which one you're given, we'll give you the other one. Again, as I mentioned a second ago, it does change with temperature, but for the most part, a lot of times you can assume 25 degrees unless it specifically says you are not at that temperature. Any questions on that there? All right, so I want you to try one here. What is concentration of OH minus in an HCl solution who has a hydrogen concentration of 1.3 molar? So here, obviously, we could use our Kw relationship. Again, concentration of H plus times concentration of OH minus equals 1 times 10 to the minus 14. Again, that's obviously something you should know, and that is a constant. Here we are looking for the OH minus concentration, so we're just going to rearrange here, and that's going to give us 1 times 10 to the minus 14 divided by the H plus concentration. Popping our number in there. We definitely want to make sure we using our exponent button as we punch these things in, and that will yield us a 7.7 times 10 to the minus 15. This does need units as it is a concentration, so it would need molarity there as the units. Any questions on that there? Let's try a couple more here, maybe. In a solution where we have an H plus concentration 1.2 times 10 to the minus 6, what will be the OH minus concentration? And will it be acidic, basic, or neutral, this solution? Okay, so let's take a look. Again, here we'll use our Kw relationship. In this particular case, we are given the H plus, so here again, we will go for our OH minus. Will equal 1 times 10 to the minus 14 divided by our H plus. We're going to divide, obviously, to that side. And in this case, that will be 1.2 times 10 to the minus 6. If you punch that in, you should get something like 8.3 times 10 to the minus 9 molar. Would be our hydroxide concentration. Or if you have a calculator, like a lot of people, including mine, if you're not in scientific notation, you got like 8 zeros and an 8 at the end because your calculator right out of room, pretty much. Yeah. So if you got that move, that's again the issue is you ran out of room on your calculator. So it just did that. Not a big deal. So if you put in scientific notation, that's how you get to the 8.3. We now want to compare our H plus concentration, right, to our OH minus concentration to determine if it's acidic, neutral, or basic in this case, and which one is larger, the H plus or the OH minus? It's very quiet. It is. It is the H plus concentration is the larger value. Yeah, everybody agree? And that would mean, I guess we would look at tier 4 as it being acidic. Just a reminder that when you look at the exponents that are negative, the one with the smaller negative exponent is actually the larger number because in this case, you're only going 6 places this way and putting zeros. This guy, you're going 9 places this way and putting zeros, which makes it a much smaller number, right? So again, that negative there on the exponent is important. And if you have a negative exponent, the smaller negative exponent is going to be the larger number. Any questions on that there? As we could demonstrate, obviously, by if we move this guy. Yeah, something like that versus something like that, right? So obviously a much smaller number here. That's a much larger number. All right, let's continue on then. Let's talk a little bit about pH. pH is the measure of acidity, and it works off the pH scale. So let's talk a little bit about this. The pH scale, for example, does run from basically 0 to 7 to 14. Anything less than 7 is acidic. Anything above 7 is basic, as I almost ran over. And really 7 on the nose is neutral, and that's where we're going to roll with in this class. It's got to be 7 on the nose, or pretty darn exactly just slightly over 7 for it to be there. So less than 0.1 above or below, we'll go with neutral, but basically 7 is going to be neutral. Anything a little bit below 7 will be slightly acidic. Anything above 7 will be slightly basic in that case. And we can calculate the pH by using this equation here. That is the pH is equal to minus the log of the H plus concentration. This is, again, another formula that if you don't like H plus, you can substitute in H3O plus. It is the same thing. By the way, 7 is kind of our central point here on the pH scale. As we go towards 14, we're becoming more basic. And as we go towards 0, we're becoming more acidic in this case. Now, when you look at this equation, it does depend, or this formula, it depends on the type of calculator that you have as to how you should punch this in correctly. So if you have a display calculator, you basically punch it in exactly the way it's written if you have a display calculator. If you have a non-display calculator, this formula and all the other formulas that we're going to see, you need to go backwards if you have a non-display calculator, which means you need to start with a number, hit log, and then hit the negative button. If you're not sure what a display calculator is, because you're looking at your calculator and they all have displays on them so you can see numbers, non-display calculator means when you hit the log button, you hit your log button, it says log, you have a display calculator. Congratulations. If you hit the log button and it says error, congratulations as well. You have a non-display calculator. Yeah. So if you hit the log button by itself, it says error, non-display. And if you have a log button, you hit the log button, it says log, you have a display. So again, depending on which type of calculator you got as to which way you need to go when you punch it in. And you want to also obviously make sure that you are using your exponent button, obviously, as you do this. So when we calculate the pH, it is just a number. And some relationships is if the H plus concentration equals the OH minus concentration, as we talked about, that means that the H plus concentration will actually be 1 times 10 to the minus 7. And that will give you an actual pH of 7, which is why 7 is actually neutral. Yeah, so 7 on the nose is actually neutral because by definition, those concentrations are actually equal to each other, and that will give you should give you exactly that number. Again, if it's slightly off of that, then it'll either be slightly acidic or basic. If you have a more H plus concentration, you will have a pH less than 7 when you put it in there. And if you have an OH minus concentration that's greater, you will have a larger value of pH above 7, basically in the basic range. The pH concentration goes up as the H plus concentration goes down, and obviously vice versa. The pH goes down as the H plus concentration goes up. Another really important relationship between, say, H plus and OH minus concentration is as one of those go up, the other goes down. So they go opposites of each other as well. And one goes up, the other goes down. And that's how they keep KW, for example, equal to 1 times 10 to minus 14, because they run opposites of each other. So again, as one goes up, the other goes down in terms of H plus and OH minus. Any questions on that? Clearly, we need to talk about the importance of significant figures, I suppose. Significant figures and pH. So your pH should have the same number of decimal places as the concentration number has significant figures. So whatever number of significant figures your concentration has is actually how many decimal places you should take the pH to. And by the way, it works backwards as well. If you have the pH and you want to calculate the concentration, however many decimal places it is in the pH is how many significant figures you should take for your concentration. So let's say we had an H plus concentration of like, I don't know, 1.0 times 10 to the minus 5. Calculate the pH to the proper number of digits. We're going to go into our pH equation, and depending on your calculator, how you're going to punch it in, you're going to hit your negative button, log button, and then go 1 exponent negative 5. So if you're going in the forward direction, again, you're going to punch it in like this. Obviously, if you're going in the other direction, you're actually going to start with the number, so you would punch that in first. You would then hit the log button, and then you would hit the negative button. So again, if you're going in that direction for a non-display versus a display. Regardless of which way you go, the pH that you get staring at your calculator is 5, to start with that part of it. Yes. Now, to report this properly, should it be 5? Should it be 5.0? Should it be 5.00? Which one should it be? The number of significant figures here is 2 significant figures. That means that I should end up at 2 decimal places. Yeah. So here we're going significant figures to decimal places, not sig figs to sig figs in terms of the rule. And this right here should be the correct way to basically give the answer. Question on that there. By the way, acidic, basic, or neutral on this guy? This is acidic, right? It's less than 7. So the pH is less than 7, which means it is acidic. Also, by the way, if you have 1 times 10 to the whatever, it will always be equal to the exponent. Yeah, if you take the log of it, basically. So if I had an H plus concentration of 1 times 10 to the minus 4, the pH here would be 4, right? Basically. And what we see is for every power of 10 change that we do, the pH changes by 1, basically. Yeah, so the pH changes by 1 for every power of 10 change that you do in that. Any questions on that there? Now there's the pH scale, and again, we could see some things. We have our sodium hydroxide here on the towards 14. We also have pure water here at 7. HCl, which is a strong acid, towards 1. Some acids in the acidic range. By the way, if I take some water out in a beaker and then I test the pH, it's been sitting out maybe for a bit, will the pH of it be 7? The answer is it will not, probably. And the pH actually will be acidic in that range. And that is because as it sits out, it collects a little carbon dioxide from the air, makes a little carbonic acid, which then will increase the H plus concentration and lower the pH in that particular case. So sometimes people are surprised. They test the pH of water and they're like, whoa, it's like not like neutral or anything like that. That is a pH meter made by a guy named Beckman. And it measures basically the H plus concentration that's in the solution. Essentially, how it works is by voltages. So you actually calibrate it and go, this is like a pH of 7, this is a pH of 10, this is a pH of 4, and they figure out the voltages for those solutions, and then makes like a little calibration curve, and then you test yours and test the voltage basically of what you got in that solution based on the H plus concentration, and comes up with a pH value. So that's a very easy way to test the pH. It gives you a digital sort of value for it. You could also use pH paper, where you dump it on the pH paper, the solution, changes color. Like if you ever tested your pool or a pool, you kind of move it around to try match up the color to try and figure out what the pH is. We also sometimes can use litmus paper, which doesn't give you the pH, but will tell you if something's acidic or neutral or basic, really. And usually of litmus paper, if it turns red, it's acidic. And if litmus paper turns blue, it's basic. So if you put a solution on litmus paper, you oftentimes will use red litmus paper and put something on it, it goes red to blue, it will be basic. And if you use blue litmus paper and put something on it and it goes from blue to red, it is acidic. Obviously, if it stays blue or stays red, then it's acidic or basic, obviously, depending on which one it is. Now, there are similar scales to pH that we oftentimes will use as well, and that is the pOH. The pOH, much like the pH here, it actually will tell you what it's measuring. The pOH means you need the OH minus concentration. So you could calculate the pOH by taking negative log of the OH minus concentration. Again, you would punch that in the same way as you did pH. Same rules apply. pH again here minus the log there of H plus. Why you might want to calculate the pH is maybe you're given the hydroxide concentration and you really want the pH. So there's a really nice relationship between those two, which is if you take the pH plus the pOH, it equals 14, which means if you're given the OH minus concentration, you could calculate the pOH, subtract 14 from it, and you'll have the pH pretty quick. Or vice versa. Obviously, if you have the pH and you want the pOH, you could also subtract it as well. So those equations are important to know, along with obviously our Kw that we saw earlier. H plus OH minus equals 1 times 10 to the minus 14. Now, in addition to these equations, we can also calculate a couple of other things, which is, we'll go this way here. So we have our pH, we have our pOH, we have our pH plus our pOH equals 14. We have our Kw, H plus OH minus. Now, if you are given the pH, directly from that, as the name would imply, you could actually get the H plus concentration directly from the pH value. And you could get the H plus concentration by taking the inverse log of the negative pH. Same thing with pOH. If you are given the pOH value, you can get the OH minus concentration from that by doing pretty much the same calculation, which is the inverse log of the negative pOH. What does that look like when you punch that in your calculator? On most people's calculators, when you do the inverse log, it will pop up a 10 and a caret, also known as how a lot of people still do scientific notation incorrectly. Yeah, so this is what you want to use it for. And on most people's calculators there, you want to use the second button, maybe the shift button that's in the top left corner, and your log button that has like that. That is how you get to that button in case you need to get there. Same thing with your calculator. If you're going to punch this into your calculator and you have a display calculator, you roll this way. You do the shift log and then negative and put in the pH. If you have a non-display calculator, you got to go backwards as well on this one. So you got to start with the number, you got to make it negative, and then do second log. So again, depending on your calculator as to which way you need to punch that in. So clearly here we have a variety of ways that we could get to an answer depending on the question. So there really is no wrong way. You could use KW if you wanted to. You could use the inverse log. It all will give you the same answers, just whichever preference you have. And kind of really whatever you kind of start calculating first as to maybe what you might use in that. So there is sort of more than one way to get to the same answer, depending on the equation or formulas that you choose. Any questions on those there? All right, let's try our calculators here, make sure they work. So, all right, so for this one, let's just do everything just to make sure. So we will look for on the first one here, what is the H plus concentration? What is the OH minus concentration? What is the pH? What is the POH? And is it acidic, basic, or neutral? Same thing down here on the second one. We want, we'll do everything. What is the pH, the POH? The H plus concentration, and the pH, I could use the pH plus the POH is equal to 14 to get me the POH, which would be 14 minus my pH in this case, and that would get me a POH of 9.18. I could, at this point as well, I could have started if I wanted to with the H plus concentration. So because I did have the pH given to me, the H plus concentration will equal the inverse log of the negative pH equals. And again, on your calculator, when you punch that in, it'll probably pop up a 10 and a caret. You want to make sure you do make it negative in this case, and 4.82. And if you do that, looks like you will get something like 1.5 times 10 to the minus 5. We do need units as this is a concentration. By the way, I had 2 decimal places, gives me 2 significant figures. Yes, again, going backwards, you want to follow those same sort of rules for the significant figures. At this point, I'm wide open for options as to how I could get the OH minus. I could absolutely use KW like we've done before. So if you wanted to use KW, you can use that, is perfectly fine. And obviously here we just got our H plus concentration. So if I do that with KW, I'll get, we'll call it 6.6 times 10 to the minus 10 molar. You could have also, because I got my POH, I could have used the POH and did the inverse log of that, of the negative 9.18. And again, you'll get the exact same answer. So it is just a preference as to sort of which way you want to go with that. And again, you'll get the 6.6 times 10 to the minus 10 molar. First off, any questions on any of those calculations? This guy is acidic, basic, or neutral? What is it? Well, the pH is 4.82. That is what you should look at, and this solution is acidic. By the way, when you are asked that question, is it acidic, basic, or neutral? There's just one answer, and that's not acidic and basic at the same time. And that commonly happens because people calculate the pH and go, it's less than 7, it's acidic, and then they calculate the POH and go, cool, it's above 7, it's basic, the same solution. So it can't be both. It's only, that could be one. I've never had anybody give me all three though. The only acid and base, never acid, base, or neutral. The reason that is, just so we're clear, why you should probably always look at the pH scale. That is because that's usually the one everybody has in their head. So the pH scale that we just saw, right, was 0 to 7 to 14, where below 7 is acidic, above 7 is basic, and again, this guy is neutral. The POH runs opposite of the pH scale. Below 7 is basic, above 7 is acidic, and 7 is still neutral. So since most people have the pH scale in their head, I would always look at the pH number and make that decision. I would not look at the pOH value and make that decision because, again, most people have that pH scale in their head. And it does run opposite. So if you have, like we see here, if you have a low pH, you will have a high pOH and vice versa. So they run basically opposites of each other. Any questions on that there? All right, we'll save the next one for next time.